Hello, and welcome to the Unit 6 study guide. So we're going to go through the entire thing here. It's going to be probably the most fun you've had all day. So let's start with number 1. How many moles of aluminum are required to produce 3.58 grams of aluminum chloride? Okay, so we've got grams, and it's asking us for how many moles. Okay, we're starting with aluminum chloride, and it's asking about moles of aluminum. Okay, so always start with the given number, which is 3.58 grams of aluminum chloride. Okay, so we're going to have a couple steps here. We're going to need 2 steps. First, we need to convert 2 moles, and then we need to convert from moles of aluminum chloride to moles of aluminum. Okay, so I'm going to need the molar mass of aluminum chloride, and that is 133.33 grams. Okay, that's how many grams are in 1 mole of aluminum chloride. And then our ratio from aluminum chloride to aluminum is 2 to 2. So for every 2 moles of aluminum chloride, we have 2 moles of aluminum. Okay, these calculations can be somewhat tricky. So what I'm going to do is I'm going to do these, maybe the first couple on a calculator here, so we can get familiar with entering these. My recommendation is when you're putting these in your calculator to do it in steps and not try to do the whole thing. Okay, so the first one's pretty easy, and I'll point out why here in a second. So 3.58. Now, the 133.33 is in the denominator, so we're going to divide by 133.33, and I'll hit enter. The second step is 2 over 2. We're going to multiply by 2 over 2. It's kind of silly because 2 over 2 is actually reduces down to 1 over 1, which reduces to 1. So any number times 1 is just that number, so we're going to get the same thing. Okay, so as far as sig figs go here, let me pull that back up. As far as sig figs go, we have 3 sig figs in our original number. So the answer that we got on our calculator was 0.02685. We want to round that to 3 sig figs. So after the decimal, that first 0 doesn't count. That's a leading 0. So it'll be 268, and then we look at the 5. So we're going to round this up to 0.0269 moles of aluminum. And there's our first answer. All right, second one says, how many molecules of aluminum chloride are in 3.58 grams of aluminum chloride? Okay, so we're given grams, and it's asking for molecules. Okay, now notice here, we are in aluminum chloride the whole time. So we don't need to convert, we don't need to use a mole ratio here to go from aluminum chloride to something else. So our given is 3.58 grams of aluminum chloride. Okay, we're going to need 1 step to go from grams of aluminum chloride to moles of aluminum chloride, and then another step to go from moles of aluminum chloride to molecules of aluminum chloride. Okay, so again, we'll use the same molar mass here, 133.33 grams of aluminum chloride. That's how many grams are in 1 mole of aluminum chloride. And then, to go to molecules, for every 1 mole of aluminum chloride, we're going to use Avogadro's number, 6.02 times 10 to the 23rd molecules of aluminum chloride. Okay, so this is going to be a good example to practice on our calculator. So let's go ahead and clear that out. So we start with the given, so 3.58. The 133.33 is in the denominator, so we're going to divide by 133.33. I'm going to hit enter. Now, the next part is scientific notation, so we'll do times. And then 6.02 times 10 to the 23rd, we enter that as 6.02. You're going to press the second button, whether you're using a graphing calculator or whether you're using one of the blue calculators that we have at school. We're going to go to E, and then I'm going to type in 23. That E represents times 10, and whatever number follows that E is the exponent. Okay, so we get 1.6164, blah, 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 E22. And again, that E stands for times 10. We're going to want 3 sig figs here, because 3.58 is 3 sig figs. So let's see, 1.6164. So it'll be 1.61, and then we look at that 6. So we're going to round this up. So this will be 1.62 times 10 to the 22 molecules of aluminum chloride. All right. Number 3. Calculate the mass in grams of 0.0450 moles of chromium. Okay, we're not going to need an equation for this one. Always start with the given. So 0.0450 moles of chromium. To go from moles to grams or mass, we're going to need the molar mass. So for every 1 mole of chromium, we go to the periodic table and look that up. And its mass is 52.00 grams of chromium. Okay. So when I put this in my calculator, I'm just going to multiply 0.0450 by 52. And rounding this to 3 sig figs, we get 2.34 grams of chromium. Okay, number 4, determine the number of aluminum atoms in 1.25 moles of Al2O3, so aluminum oxide. So let's see, we've got 1.25 moles of Al2O3. All right, we're going to need to go from moles to particles. So 1 mole of Al2O3 contains 6.02 times 10 to the 23rd atoms of Al2O3. So when we do this on our calculator, we get an answer of 7.5275 times 10 to the 23rd molecules, atoms. No, molecules. Well, it doesn't matter. They're particles one way or another. Okay, of Al2O3. But if you look on here, it's asking for specifically aluminum atoms. So in the molecule, we have two aluminum atoms per molecule. So we need to multiply this by 2. So when we multiply that, we get 1.51 times 10 to the 24th aluminum atoms. All right, the next one is very similar. Determine the number of nitrogen atoms in 3.89 grams of nitrogen oxide. So 3.89 grams of N3O6. We're going to first need to convert this to moles, and then we'll need to convert the moles to atoms, okay, or molecules rather. Okay, so the molar mass of our nitrogen oxide is 138.03 grams. That's how many grams are in 1 mole. And then 1 mole contains 6.02 times 10 to the 23 molecules of N3O6. Okay, so when we do this on our calculator, we get 1.697 times 10 to the 22 molecules. Each molecule has 3 atoms. So when you multiply that by 3, you get 5.09 times 10 to the 22 nitrogen atoms. All right, moving right along here. Number 6. Okay, so we've got a bunch of data here, and it's asking us a bunch of questions about it. So we've got a crucible. Remember, the crucible is those things that we heat stuff in. Okay, so we've got the empty crucible, and then you've got some mass in it. Okay, so if I wanted to get the mass of that, I would basically take the empty container minus the full container. I get the difference between them, and that would be the mass of the content, or the mass of the contents. Yeah, that's what I meant. Okay, so empty crucible is 12. So let's go through and let's subtract 12 from everything. Okay, so 15 minus 12 is 3 grams. 14.3 minus 12 is 2.3 grams. And let's continue on. This is going to be 1.9 grams, and no change here, so this will also be 1.9 grams. Okay, so that's the contents of the container after each process. So what's the total amount of water lost through heating? Okay, so after heating, so it starts with, let's see, 3 grams when it's full, minus 1.9 when it's done heating. So that gives us a difference of 1.1 grams of H2O that we lost. Okay, so we heated it and the water evaporated off, and we're just left with 1.1 grams of water that was lost. Okay, so 1.9 is everything that was left over after we heated it off. Okay, it says what is the percent of mass of water in the compound? Okay, so that'll be like the water lost over the total mass times 100. So we lost 1.1 grams. The total mass was 3 grams times 100. Plug this in our calculator, we get 37%. Okay, a student is using a hydrate. What is the percent by mass of water in the hydrate? Okay, so let's start by calculating our molar mass. So we've got copper, 63.55 grams. We have chlorine, there's 2 of them. Each one is 35.45. And then we have water. Water I've done a bunch of times. Water, there's 3 of them. Each one is 18.02. So our total molar mass of the whole hydrate is 188.51 grams per mole. Okay, so that's the whole thing. And it's asking what percent by mass of water is hydrate. So that's going to be the mass of water over the total mass times 100. So the mass of the water, so 3 times 18.02 is 54.06. So 54.06 grams over the total, which is 188.51 grams, times 100 is 26.68%. So of the whole thing, 26.68% is water. All right, the empirical formula of a compound is CH2. Its molar mass is 70 grams per mole. What is its molecular formula? Okay. So remember, empirical is the simple form. Molecular is usually the molecular is the empirical formula and then some multiplier. So we're going to need to figure out the molar mass of the empirical. So we got carbon, we have hydrogen. Carbon is, let's see, carbon is 12.01. Hydrogen, there's 2 of them. Each one is 1.01. So let's just call that 14 grams per mole. It's close enough. So we're going to do the molar mass of the empirical over the molar mass of the molecular. So the empirical, wait a minute. I have that backwards. Do that every time. Okay, it's the molar mass of the molecular over the empirical. It's always the bigger number on top. Molecular over the empirical. Okay, let's try that again. So 70 is the bigger number, it goes on the top. Empirical is the smaller number, it goes on the bottom. 70 divided by 14 is about 5. So this number right here is your multiplier. So we're going to multiply the empirical formula, which is CH2, by 5. So 1 times 5 is C5. 2 times 5 is 10. So this will be our molecular formula. All right, compound is 69% carbon, 13.5% hydrogen, and the rest oxygen. Molar mass or molecular mass is 222.4 grams per mole. Determine the empirical and the molecular formula of the compound. Okay, so 100 minus 64.9 minus 13.5 means our oxygen is going to be 21.6%. Anytime you're working with percents instead of grams, you want to do this. You want to assume there are 100 grams. So our percents are going to just be the grams. So for carbon, it's going to be 64.9 grams of carbon. For hydrogen, it's going to be 13.5 grams of hydrogen. And then for oxygen, it'll be 21.6 grams of oxygen. Okay, carbon is 12.01 grams for every 1 mole. Hydrogen is 1.01 grams for every mole. Oxygen is 16 grams for every mole. Okay, so doing the math here, we get 5.4 moles of carbon. We're going to end up with 13.4 moles of hydrogen, and then 1.35 moles of oxygen. Our next step is to divide by the smallest number of moles, which is 1.35. Okay, in doing so, we get about 4 here, we get about 10 here, and then of course this will be 1. So our empirical, we just take these numbers here, and those are going to be our subscripts. So C4, H, 10, and then O. We're not done yet because it wants the molecular formula as well. So I need to know the molar mass of this. So figuring out the molar mass is going to be 74.1 grams. So I'm going to do it right this time. It's going to be the molar mass of the molecular over the molar mass of the empirical. Molecular is 222.4, empirical 74.1. My multiplier will be 3 this time. So I'm going to take my empirical formula, C4H10O, and I'm going to multiply that by 3. So my formula will be C12H30O3. That's my molecular formula. All right, moving right along. Wow, this is so much fun. Okay. All right, number 10. 2.65 gram sample of a compound has the following composition: 0.7 grams of chromium, 0.65 grams of sulfur, and 1.3 grams of oxygen. Determine the empirical formula of the compound. Keep 4 significant figures when determining the number of moles. Okay, so we don't have percents this time, so we can skip that step and we can start right with the moles. Sorry, right with the grams. So let's see, we have chromium, so 0.70 grams of chromium. We have 0.65 grams of sulfur, and then 1.30 grams of oxygen. Let's go ahead and let's convert those to moles. So chromium, let's see, 52 grams for every 1 mole of chromium. Sulfur, we have 32.07 grams for every 1 mole. And then oxygen, 16 grams for every 1 mole. All right, so doing the math here, we get 0.01346 moles. Okay, again, the directions tell us 4 sig figs. Here, 0.02027 moles. And then for the third, 0.08, it's a 125 moles. Divide by the smallest number, which is our top number, so 0.01346. Do that to each one. Okay, so for the top we get 1. Here we get 1.5, and then down here we get 6. Okay, it's only asking for the empirical formula. So let's see, that'll be chromium 1, sulfur 1.5, and then oxygen 6. Okay, but we can't have this. That's no good. Can't have a decimal, so let's multiply the whole thing by 2. So we'll get chromium 2, sulfur 3, oxygen 12. Okay, that will be our empirical formula right there. All right, the molecular mass of the compound in problem 10 is 392.2 grams per mole. What's the molecular formula of the compound? Okay, well, we need the molar mass of our empirical formula. And this one is actually 392.2 grams per mole, which is the same as this. So remember, it's the molar mass of the molecular over the molar mass of the empirical. So 392.1 over 392.1 is 1. So our molecular will be the same as our empirical, which is Cr2S3O12. All right, determine the theoretical yield of potassium chloride if you started with 34.5 grams of potassium carbonate. All right, well, potassium carbonate is this, and it's asking us for the theoretical yield of potassium chloride, which is this. Let's see, 34.5, always start with the given. Okay, so 34.5 grams of potassium carbonate. Okay, we're going to need 3 steps here. I'm also going to need to learn how to draw straight lines. Okay, so we need the molar mass of potassium carbonate. That is 138.21 grams. Okay, that's how many grams are in 1 mole. Now, coefficient-wise, we're going to need to do a mole ratio here. There's no number there, and we have a 2 here. For every 1 mole of potassium carbonate, we have 2 moles of potassium chloride. Now we need to determine the number of grams of potassium chloride. For every 1 mole of potassium chloride, we are going to have its molar mass, which is 74.55 grams of potassium chloride. Okay, I'm going to go ahead. I know it's been a while since I've done one of these on a calculator, but I'm going to go ahead and do this one on the calculator just because these can be kind of tricky to do. So let's start with the given. So 34.5. 138.21 is in the denominator, so we divide. Okay, we're going to multiply by 2 over 1. So we'll use parentheses. So 2 divided by 1. And then we finish this off by multiplying by 74.55 because it's in the numerator. Okay, so there's our answer. We're going to run around this to 3 sig figs. So in rounding this to 3 sig figs, we get 37.2 grams of potassium chloride. Using the reaction in number 12, if a student isolates 33.4 grams of potassium chloride, what is the percent yield? Okay, so formula for percent yield is actual yield over theoretical yield times 100. Okay, so the actual yield would be what we got in the lab. So 33.4 grams over the theoretical. The theoretical is what we calculate is possible, 37.2 grams, and then we multiply that by 100. Okay, in doing so, we get an answer of 89.8% yield. All right, now we're moving on to the big leagues here. Okay, so this is the culmination of the unit. 200 grams of each reactant are used in the lab according to the following reaction. Okay, what amount of sodium chloride can be produced? So we have 2 reactants. We have sodium, we have chlorine. We want to figure out how much of the product we can make with each ingredient. So let's start by doing the sodium. So we have 200 grams of sodium. Okay, we're going to need 3 steps because we're going to go from grams of sodium to grams of sodium chloride. Okay, so sodium has a molar mass of 22.99. Okay, that's how many grams are in 1 mole of sodium. And then the ratio, so there's a 2 in front of the sodium, so 2 moles of sodium for every 2 moles sodium chloride. And then each mole of sodium chloride has a molar mass of 58.44 grams of sodium chloride. Okay, plugging this in on our calculator, we get an answer of 508.4 grams of sodium chloride. We're going to do the same thing with chlorine. So for chlorine, again, 200 grams. Okay, 3 steps, just like before. Okay, actually this isn't just chlorine, this is Cl2. Okay, so Cl2 has a molar mass of 70.9 grams. That's how many grams are in 1 mole of Cl2. Our ratio is 1 mole Cl2 for every 2 moles NaCl. And then each mole of NaCl has same molar mass as before, 58.44 grams of NaCl. Okay, so when we do this on our calculator, we get 329.7 grams of sodium chloride. Okay, so the most we can make is 329.7 grams. We have enough sodium to make more of our product, but we're limited by the amount of chlorine. Even though we have 200 grams of each, we need more sodium than we do chlorine. Sorry, we need more chlorine than we do sodium to make this. So our limiting amount is going to be the chlorine, and we're only going to be able to make 329.7. Okay, so the limiting reagent or reactant is going to be our chlorine. Our excess will be the sodium. And our reasoning would be the limiting reactant makes less product. Chlorine's going to run out after we make 329.7 grams of our product, but we're going to have extra sodium left over. So that's why sodium is our excess. Calculate the percent yield of our reaction. If we go back up to the data table, we have 2 other numbers that we haven't used yet. We have the mass of the empty beaker, and we have the mass of the beaker plus the product. We're going to want to subtract those. So our actual yield is going to be the mass of the beaker plus the product, which was 385.99 grams. We're going to subtract the mass of the empty beaker, which was 122.23 grams, and we get 263.76 grams. Okay, that's our actual yield. Percent yield is actual over theoretical times 100. So actual, 263.76 grams. And then our theoretical, if we go back up here, the most that we can make is 329.7 times 100. We get 80%. That's it. Got this. Good luck.